So I'm sure all of you are waiting for the next plenary by Dr. Jim Bell. Um, Jim, I didn't see Jim this morning. Jim, are you here? Okay, great. Oh, he is great. Okay, so I'm going to start to introduce Jim. So Dr. Jim Bell is a professor in the School of Earth and Space Exploration at Arizona State University. And he's the president of the Planetary Society, and he's involved in many NASA space mission exploration, and he's the lead scientist on the PanCam camera. It's the color stereoscopic imaging and panoramic imaging on several missions of NASA, and has been involved with many of them, such as Any Opportunity, Spirit, and what else. In addition, he's a prolific writer and has been writing in several science magazines. And also, he appeared on several medias and interviews. For example, he recently had a TEDx talk. In addition, he appeared on NBC, CBS, Discover Channel, National Geographic, what have you. He even appeared in Australia, 60-minute show. Who's from Australia here? So, yeah, so he appeared 60-minute show in Australia. And also, guess what? He has a belt asteroid named after him. Yeah, 8146 Jim Bell. So he's pretty amazing, and I'm looking forward to his talk also. It seems he's working on his slide now, but yeah. So we'll wait for Jim. Oh, yeah. Okay. So please. Thank you. It's an honor for us to have Dr. Bell here.
Nice to meet you. Thank you so much. Thank you. Our colleague here is going to set up my laptop, and so I'll say a couple of introductory remarks. First of all, I want to thank the meeting organizers for inviting me to present today. And I was listening to your society president talk about the real world problems and issues that you're all dealing with and tackling in signal processing. Those are part of my world too, but lately my world and the world for many of us on campus here in Tempe has been the red planet on Mars. And so there are a wide variety of signal processing issues that we have to deal with and tackle there. Hang on a second. Okay. So I'm a professor here at ASU in Tempe. I'm in the School of Earth and Space Exploration. And let's see if I can get this connected. And I'm a representative of a large number of people who, from ASU, other universities around the country, universities and government labs around the world, who are actively working on collecting images and other data from space missions like the Mars rovers. And so if my computer stops giving me the beach ball of death, I will be showing you some examples of some of the imaging data and other measurements that we take from these vehicles. Stand by. Ah, hooray. That's good. Now let's see if we can get it up on the screen there. Are you receiving me, back room? Yes, that's a good sign. Yes, hooray. Oh, wait, come back. Okay, great. I think we're good. And I've got, I can advance, and I don't have to point, but I can advance slides. Yes, I can. Okay, good. Okay, thank you. Good morning. We are up and running. So we're roving on Mars with robotic vehicles. What I'm going to talk about focus on today is some of the imaging results, and talk about some of the challenges and opportunities as they go along in the image processing world writ large that we deal with these particular vehicles. And there are a lot of challenges, maybe one of the most important of which is that essentially, we're not using the same technology as all of you because we're like 10, 15, 20 years ago kind of technology. NASA is an extremely conservative agency when it comes to launching things into space. Their policy is essentially you can't launch it into space unless it's already launched into space. And that makes it very difficult and very slow to advance the frontier of technologies like imaging technology. So I'll talk about some of the sensors and techniques that we use, and some of you may think, oh my gosh, that's ancient history. But it's really not fair to judge it in the same playing field as the technologies many of you are working on, which go quickly from the lab or the coding you're doing right out to product. It's very difficult to do that in the space world. But yet we move on. It's really a story of that technology and how it interacts with this enigmatic planet, Mars, the fourth planet from the sun, the next one out from the Earth. A very interesting and enigmatic place because it has a thin atmosphere, much thinner than the Earth's, mostly made out of carbon dioxide. An ancient surface, heavily cratered terrain as revealed by orbiters and flyby missions over the past 40 years, more than 40 years. So in some sense, parts of Mars look like the moon. In other senses, parts of Mars look like some of the most amazing geologic landscapes on the Earth, the largest volcanoes in the solar system, the deepest canyons in the solar system, enormous river channels flowing across the surface in the most ancient parts of Mars, telling us that liquid water flowed across the surface of this planet a long time ago. And also some places where, and this is a very small, few 100-meter wide region on the side of an impact crater, regions where water may be flowing across the surface even today, very young areas. And this is an enigma because today, Mars is this very cold, very dry, ultraviolet bombarded, lifeless as far as we can tell on the surface place. It is, despite some Hollywood depictions, it really is a hostile environment. It looks like, in pictures you'll see, it looks like it could be somewhere here in the desert Southwest in many ways. But just like in the movie The Martian, Mars would be trying to kill you in so many ways. It's a very hostile environment. And even though it's the most Earth-like planet out there, besides the Earth in our solar system, it's very, very hostile and very different than the Earth. But the hypothesis that drives NASA and other space agencies to explore Mars is that this place that we see today with our orbiters and landers and rovers, a long time ago, if you turn the clock back to that time when liquid water was flowing across the surface 3-4 billion years ago, may have looked something like this, an artist's depiction, filling in the low regions with water. We know there was liquid water there. We know there's water ice there in the high latitude regions. We know there's water vapor in the atmosphere today. And so the question is, what happened to all this water? Where is it now? Did the planet lose it? Is it in the subsurface? Is it extractable? Is it trapped in the rocks and minerals? And what can we learn about what this environment was like back then by studying the place today, from telescopes or going there up close with robots and eventually going there with people? It's a hypothesis that Mars was a more Earth-like planet, that it was warmer, that it was wetter, that it was habitable for life as we know it. And there are ways to test that kind of hypothesis. Of course, the best way to test it would be to go there with a gang of field geologists and our graduate students to do some work, but we can't go yet, right? The depiction in the movie The Martian, that happened in the 2030s. That might actually happen. It's about the right time scale, the 2030s. But right now, we're kind of stuck having to send our silicon-based emissaries, our robot geologist friends like Spirit and Opportunity here. You can see the size of this vehicle. This is in the laboratory at JPL. And it's kind of non-intuitive to think of these vehicles as spacecraft, right? We think of them as cars, But they're spacecraft, power systems, comm systems, instrument systems, propulsion systems, if you will, independently self-reliant for their day-to-day operations, but in communication with us and being commanded by people on the Earth. So that's Spirit and Opportunity, and the most recent rover, Curiosity, a little bit bigger, about the size of a Mini Cooper. Same kind of basic technology, though. And mobility is absolutely critical. So this has really allowed us to ramp it up a notch compared to the original Viking landers in the 1970s or other landers that have gone to Mars. Because what we're trying to do is test that hypothesis, and that's essentially forensic field geology. And a field geologist would never get dropped out of their helicopter in the middle of some field site and just kind of stand there and try to reach, right? You move around, climb to the highest hills, get the lay of the land. And so that's been an absolutely critical part of these rovers. And we've used that mobility as a tool, as an instrument in our endeavors. You outfit these vehicles, these spacecraft, with the best possible technology. Spirit and Opportunity are kind of late 90s, very early 2000s technology. As you'll see, we do remote sensing with cameras up on the mast. We have this arm with some instruments on the arm that will allow us to take microscopic scale images, APXS chemistry data, some other mineralogy data, and then communication systems that can communicate directly to the Earth, although that's a weak signal and very, very rare, very low bandwidth. Most frequently, we communicate to orbiters around Mars, in Mars orbit, much stronger signal, much higher bandwidth, and those orbiters relay data back to the Earth. But we're only talking about hundreds of megabits per day, hundreds of megabits. So we basically have, dial-up connectivity, if you remember what that is. The young people in the audience won't remember. What's dial-up? Ask somebody older next to you. We have dial-up connectivity to Mars. We don't have high-speed internet, and that's a real restriction. Here's the cameras that we operate from campus in Tempe here, the color cameras on Spirit and Opportunity. The Opportunity rover is still operating. It landed in January 2004. Today is Opportunity's 4,506th day on Mars of its 90-day mission. So very, very successful vehicles. Very simple cameras, fixed focal length. Look at the optics design there. Very straightforward. You can hold them in the palm of your hand. Little filter wheel, 8-position, 8-filter imaging. The technology, again, goes back to 1024 by 2048 frame transfer CCD. It's like, wow, that's so old. But at the time, right, we were developing these things in the mid-90s. This was pretty high tech. To send a megapixel array out into deep space was fairly unprecedented for NASA. So pretty simple, straightforward frame transfer CCD, 16-degree field of view, 8 filters. We had some onboard ability to do image compression. Wavelets were a big deal. Some of you may remember back in the 90s, and some onboard image processing. But pretty simple, straightforward, and it's been working great. We've taken nearly 300,000 photos on Mars in what is a much higher radiation environment over the past 12 years with these cameras. So we put the filters in front of them, in front of the cameras, and we do narrowband imaging with these cameras. So they're monochrome CCDs. Narrowband imaging gives us these dozen or so specific wavelengths to look at, and so we're going beyond just RGB, right? We're using the fact that silicon's sensitive out to just a little bit longer than 1 micron. And those narrow bands allow us to distinguish different kinds of rocks and minerals. So we're looking at iron oxides or pyroxenes or iron-bearing silicates, common rock-forming minerals on a planetary surface like Mars. Mars has many of the same kinds of minerals that you find in volcanic environments or alteration environments on the Earth. And then we carried this little calibration target, this little sundial-like target with color chips and grayscale that allow us to calibrate the cameras directly. So is there anything green on Mars? The answer is yes, this tiny little chip of that calibration target. That's green. And we know it's green, and so you take a picture of it, use the right filter combination, put it together in an image processing program, and if it comes out green, you've done your calibration correctly. If it comes out blue, red, yellow, the right grayscale levels. So pretty simple concept. Bring something you know and prove to yourself that you can get the right kind of picture of it. Curiosity builds on that. Little better technology, sort of mid-2000s technology instead of late 90s technology, has a different suite of instruments, much larger vehicle. It's got an organic chemistry set inside, an X-ray diffraction instrument inside the rover. But the cameras up on the mast, still CCD-based, multispectral imagers. You see the little laser beam zapping out of a LIBS instrument up on the top of the mast there. It's actually an infrared laser, so you wouldn't actually see that unless you had infrared eyes. But a sort of a beefed up payload and a little bit beefed up cameras as well. Somewhat more complex, focusable. Actually, we had designed zoom cameras for Curiosity. They turned out to be too technologically challenging to build as a 15-to-1 zoom system in a very small package and have it survive a launch and a landing in the harsh thermal environment of Mars. So that had to be de-scoped back to two sort of myopic views, one narrow, one wide angle. So if you look at selfies of Curiosity, you'll notice that one eye is bigger than the other. So there's a wide angle on the left and a narrow angle on the right. Relatively simple optical schemes is shown there with the focusable elements. That was a new twist, being able to focus instead of a fixed focal length and large depth of field, being able to increase resolution, decrease depth of field, but have that focusing capability. And this uses the 1648 by 1200 HD format CCD. Kodak, or became TrueSense, now it's on semiconductor, right? But it's the same, they still make this CCD. It's a great device. And there's a Bayer pattern filter imprinted on top of the CCD. So we have this, here's just a schematic of the focal plane. There's that RG1G2B unit cell that you're familiar with the Bayer pattern. That's sitting right on top of the CCD with micro lenses. We've got two of them. They're separated by 24 centimeters or so. One long focal length, one short focal length. We have a similar onboard calibration target, and we decided instead of going with DCT, going with wavelets, we're going with DCT JPEG compression on this system, just much more easy to implement in the electronics and some onboard image processing. And I'll talk about the JPEG compressor as a challenge. So this CCD has that QE curve that I show there. So again, we exploit the sensitivity out into the near infrared, the shortwave near infrared, because there are different kinds of important to testing that science hypothesis rocks and minerals that show solid state absorptions out there. So a big challenge here is imaging in narrowband filters through an RGB Bayer pattern, right? It had never been done before. You might think it's kind of a crazy thing to do. The PI really wanted to make sure that in one of those filter positions, you just got pure RGB Bayer pattern filters, just like you would get with your cell phone. So we'll take a color picture, just like someone would do with your cell phone, do a simple white balance, and you'll get a very quick color view of the scene. But a number of us also wanted to push the sensor's capabilities out to 1 micron, and that meant using different narrowband filters that have to look through that Bayer pattern. So we've got the RGB Bayer pattern imprinted upon the QE of the CCD. Many of you are familiar with that. And then we stick in all these additional filters. So there's the RGB pattern under there, and then a bunch of these narrowband filters. And what ends up happening is that we have some filters that are only lighting up certain RGB pixels in that region short of about 700 nanometers. But at the longest wavelengths, the beautiful thing about that Bayer pattern is it's entirely transparent. The sensor just sees right through those pixels, and so we get full resolution images at the longest wavelength with this sensor, and then challenges at shorter wavelengths. You can see an example of a raw image there. It shows the imprinted Bayer pattern in raw data, and that's because Mars is the red planet, right? So the blue pixels don't light up very much. There's not a lot of blue light there, right? All that blue light is being absorbed before it's reflected back. So we use interpolation. We have an onboard ILI scheme that we use, and on the ground, if we can return the raw data, if we can afford the bits to get the raw data down, we can do much more sophisticated interpolation. But again, many of you work with interpolators. You know what the cutting edge of interpolation technology and programming is. We're stuck in the mid-2000s having to freeze the technology and without being able to update that because our computer is at 150 million miles away, being run by an extremely conservative and very good group of engineers. So it's a challenge, and it's a little frustrating too when you keep up with how the technology is advancing in terrestrial applications and realize that we're kind of stuck. But it's true for everything that NASA and other space agencies do. I mean, goodness gracious, they're still operating the Voyager spacecraft. They're out in 120 astronomical units with 1970s technology. So you get done what you can get done. You have to freeze the technology and send it on its way. We use this calibration target just like for Spirit and Opportunity, same kind of thing. A challenge here is that target's getting dusty over time. When this rover was brought to the surface, or retro rockets were firing from the landing process, bringing all kinds of dust and junk up onto the deck. You can see how dirty the deck is getting there. So that's a challenge too, is that we have to apply a model to our calibration source to correct for that. But we get by. Where do you send these things, right? So we have 2 rovers that were launched in 2003, Spirit and Opportunity. And Spirit was sent to, and remember, they're designed to try to test this hypothesis about early Mars and whether it was really warm and wet and habitable. So we sent Spirit to a big hole in the ground about the size of Connecticut called Gusev Crater that you can see it has that beautiful channel flowing into it, and it goes downhill into that hole, and there's no exit from that hole. So that's a basin, and there was water that carved that channel, and we believe it was a crater lake at one point in time. So what a great place on Earth. That would be a great place to test this hypothesis about the presence of watery materials and habitability. And Opportunity has gone to a very different place, as you'll see, very, very flat, but with a mineral signature from the mineral hematite, Fe2O3, that was discovered by Professor Christensen and his group right here at ASU using the Mars Global Surveyor orbiter. And it's a fairly unique mineral deposit on Mars. And on Earth, this mineral is often associated with places where liquid water has altered volcanic rock. And so there's kind of a mineral beacon saying, hey, land one rover here, you'll test that hypothesis with mineralogy. Land another rover here in this crater lake, you'll test that hypothesis with geology. And Curiosity launched more recently, landed more recently, also to a big hole in the ground, also looking at that geologic testing of the hypothesis, but a very different kind of place than where Spirit is, because there's this enormous pile of sedimentary rock in the middle of that crater. And it's not just the rebound central peak of an impact crater. It is finely layered sedimentary rocks. And this, those kinds of things, like around here, Grand Canyon, other parts of the desert Southwest, the sedimentary rocks that are finely layered make geologists just salivate, right? They are the pages of a book waiting to be read. And here's a place on Mars where a big chunk of that early history of the planet is preserved in the sediments. So the idea is drive the rover over there and just like walking up from the bottom of the Grand Canyon, follow the trail up, going through all those sedimentary layers coming through that early period of Mars history. So you take your cameras and you take your other instruments and your rovers and you fold them all up like origami and you put them on top of a bomb on purpose. And you watch them launch, and you're sitting there with 500, 1,000 other people who've worked for 3 to 5 years in these things, and you try not to throw up, and you just hope that they work, and sometimes they do, and that's pretty amazing. So we got them down onto the surface. Let me just show you some of I call them postcards. We call them postcards from these rovers because it was almost like we had some friends out there going to this exotic destination. What a crazy trip. And they're sending us these postcards back, showing us what they're doing. Of course, we're in control of them. The robots aren't doing the exploration. It's people doing it. But a lot of them are just really purdy, right? That's Southwest language. A lot of them are composed photographically, which we've never had a chance to do. A lot of them are historic, first time we've seen this, scientific value for all of them, and of course all of them have a story behind them. And between Spirit, Opportunity, and Curiosity, we're approaching 500,000 pictures now and mosaics back from these vehicles. So just give you some highlights from what Spirit has done in Gusev Crater. So here's the path of exploration. There's the center of that crater there. We landed very close to the center and followed the yellow line across the plains and up into those hills called the Columbia Hills, down the backside of those hills to a place called Home Plate in the lower right, which is where Spirit's mission ended about 6 years ago. So 6 years, 7.7 kilometers of travel for, again, the manufacturer's warranty from our engineering friends at JPL was these rovers will last at least 90 days on Mars. And we hope we can drive 500 or 600 meters. So just some spectacular engineering. Here's a mosaic from those little cameras I showed you, the PanCam imaging system of our lander. So Spirit and Opportunity landed with those airbags, that airbag landing system, bringing them down onto the surface. The airbags deflated. They got very dusty and very dirty. These flower petals open on the lander, and the rover drove off this lander. So this is just a sort of a historic photo of an alien artifact on another planet, right? We're the aliens. That's not our planet. And I think it's also one of these human historic sites, historic landmark, right? It's going to be there forever. It'll be part of the Smithsonian Museum on Mars someday when people go, right? But it was cool because we didn't really know what the landing site was like in detail. We were hoping there weren't these big, giant sand dunes because we wouldn't be able to use that mobility, or giant boulders. And indeed, we could see that this was a traversable terrain, which is good. And we could see these beautiful hills a couple of kilometers off in the distance, and lamented the fact that we'd never be able to get there, never imagining that we'd be on the other side of those hills one day. But you also get the sense that this picture is also on the cubicles of many of my engineering friends, because there's so much that went into these. It's not just rocket science, right? It's welding, it's wire wrapping, it's cables, it's sewing, it's mechanical engineering, lots of components and parts, and just takes a huge team of people to bring this together. One of the biggest challenges is lighting, of course. We have a simple auto exposure algorithm on board that we can use to take an image, test its exposure levels, revise, take an image again. But it takes many seconds to read that array out, and so the more that we have to use auto exposure, the slower it is to take large panoramas, and that really bogs us down with that sort of late 90s technology. So lots of times we have to guess, lots of times we have to use time of day to allow us to get details. So this is a very late in the afternoon image of some volcanic rocks that we found where Spirit landed, and you can see the textures in there because of the low sun angle. It's kind of a risky thing to take a picture at this time of day because this solar-powered vehicle, the sun is low, there's not a lot of power, you have to dip into the batteries, but the batteries have to be fully charged going into the night because it's going to be minus 110 degrees out at night, every night, and you've got to keep the electronics above about minus 40 inside the rover, so we need those batteries to survive every night. So there's a challenge you never even think about. Taking a picture puts the mission at risk. What's up with that? That's kind of crazy. This also is part of another story that, the hypothesis was that this is a crater lake, and we landed down there and we found all of this bone-dry volcanic rock everywhere we looked. So while the nation is like jumping up and down, oh, go America, go JPL, yay, and it's like this huge success, you've got a bunch of depressed scientists in the other room thinking, oh man, it's just volcanic rock. Where's this watery evidence of this possible past habitability? We weren't finding it. Lots of volcanic rock everywhere we looked. And how do we know it was volcanic rock? It's because there's not just imaging that's going on these vehicles. In fact, most of the deep science comes from what I call the squiggly line instruments, which are sitting out on the arm, the X-ray spectrometer, the alpha particle spectrometer, Mossbauer spectrometer, other instruments on Curiosity as well. And these don't take pictures, these produce squiggly lines, right? And so The detailed geochemistry information, the detailed mineralogic information comes from the spectroscopy that's being done. Something that is often not widely appreciated in the general public, of course, because people love to look at pictures. We do use some of the pictures, especially those longer wavelengths, to do some multispectral imaging that gives us some sensitivity to different kinds of rocks and minerals. But the really deep, detailed geochemistry that's coming from all of these missions comes from these kinds of spectrometers. So it's a very, very important part of the investigation, even though by data, it's a very small fraction of the bandwidth being used for these kinds of measurements. So we build big panoramas as we go, right? That 15-degree field of view, we march it along, take series of images, downlink them, put them together on the ground into mosaics as quickly as we possibly can, because we have a one-day turnaround, and then we have to decide where we're going next with the rover. So this is Spirit at the top of those hills that were along that yellow path that I showed. We decided to head for the hills because everywhere around us was this volcanic rock. We weren't seeing anything different or related to watery history. It's a very windy place up there, just like hills and ridges on the Earth. You can see the sand dunes and the scour marks in the rock. And the unanticipated and beautiful thing about this was, so we've got a solar-powered rover, solar panels. They're getting dusty from the dust in the Martian atmosphere, and we're watching our power go down slowly because they're getting coated with dust. We get up on these ridges, and the wind blows and clears the dust off. It's like, whoa, hooray, extra life. So that has happened multiple times on these vehicles. So we made that long trek across the plains there, up into those hills. They're about 100 meters or so above the plains, figured out that the rover could climb, went down the other side to this circular raised structure you can see on edge here called home plate. And here's where we started seeing some really interesting things. You can see that it's very finely layered, almost laminated. It looks like it is the result of, we think it's from volcanic ash eruptions, piling up layers of ash over time as those eruptions kept going. And it probably built up a cinder cone in this area, but that was billions of years ago. And it's very easy to erode material, and it's been eroded down over time. And all that's left is this root, this ancient root of this cinder cone. The exciting thing is on the Earth, those environments are often associated with hydrothermal alteration, places where you can alter the original volcanic rock into different kinds of diagnostic minerals, and we saw some of them on Mars. We saw, because, and this was again another lucky accident, the right front wheel of the vehicle stopped working, the motor stopped working many years into the mission, so we couldn't drive forward anymore. We had to drive backwards and drag that wheel through the soil, and as we're dragging it, it's trenching, exposing this subsurface material that we would not have seen otherwise. And it turns out it's loaded with sulfur, sulfates, and some of it's loaded with silica. And those are the kinds of minerals that you find in places like Yellowstone, where you have hydrothermal alteration, water, hot fluids, gases, and volatiles coming out of the interior, just like on the Earth. So we found this mineral evidence. The pictures tell us where to point the spectrometers, get the squiggly line confirmation that you can publish in Science and Nature magazine, and that tell us that there was water in this environment. It was hot water interacting with the rock, forming interesting minerals. A lot of that water is still preserved in the mineral structure. So this is why we spent years of this mission driving around this place, looking for more of that evidence of what the early environment was like. Up and over it, down, across, around. And this is one possibility that maybe 3.5, 4 billion years ago, this environment was a lot like Grand Prismatic Hot Springs or some other hydrothermal environment on the Earth, which of course is a great environment for biology. Simple organisms love these kinds of environment, nutrient-rich, heat, energy available. And so the question is, was this the kind of environment there on Mars? We can't test for organic molecules with these two rovers, but what we know is that there were heat sources, there was liquid water. If we infer the presence of organic molecules, those are the things required for a habitable environment. So that was a pretty exciting result. What eventually killed Spirit was that dust. So when we landed, this is a selfie pointing the cameras down, looking at those solar panels in 2004, and then in 2007, and then in 2010. It's like the rover's disappearing into the background, right? Those wind gusts were less and less frequent. And eventually our power levels dropped so that when we got stuck in a pretty deep sandy deposit, you can see the locked right front wheel here, we're driving backwards, and the left wheel spinning through these sandy sedimentary, or these sandy deposits, and it's crusty. You can see the rear wheels here breaking through that crust. That was many weeks of wheel spinning represented in these time lapses, and the power levels are dropping, and it's going into winter on Mars, and so eventually we did not have enough power to continue to drive, and the rover got bogged down and stuck. Very frustrating, because this is our last color picture from those PanCams on Spirit, and incredible amount of detail, mineralogy and geology going on here, but that was where the mission ended. There was an internet campaign to try to free Spirit. Didn't work out. The rover is still there. We can still see it from orbit. Nobody's taken it. The wheels are still on it. And it's again, an alien artifact in another world, having done its job of helping us discover that there were habitable environments on Mars. Meanwhile, Opportunity, Spirit's twin, landed on that other side of the planet where those mineral deposits were found, and still operating. 4506 is today's day. Almost 43 kilometers of driving from crater to crater to crater, driving around among clay mineral deposits today. Here's where we landed, in a very small crater, smaller than this room. Those airbags bounced across the surface and ended up rolling into this little low depression, kind of a lucky hole-in-one. Along the walls of this depression, we could see these outcrop rocks. And this was the first time we'd seen outcrop on Mars. And that's another word that makes geologists salivate, looking at rocks formed in place. So driving off the rover, looking at the ground around these outcrops, seeing the ground covered with these little tiny spherical grains, very, very strange, almost alien environment, right? What's going on here? And these little grains, we think, are a kind of a mineral deposit called a concretion. Very difficult to, I'll explain that in a moment, very difficult to measure their chemistry because they're so small. The footprint of the instruments to measure chemistry is many centimeters, and these are millimeter-sized grains. So we had to get lucky. We found a place where there was a little rock, a depression in a rock, and a bunch of these little BBs, ball bearings, blueberries, were rolling into the depression in the rock. So there's a collection of them. So we put the instruments on the collection, then put the instruments on the rock without them, and made a differential measurement. And there's a Mossbauer spectrum on the left, and the red spectrum is with the blueberries, and the blue spectrum was without, and there's a huge difference. And the difference has to do with the mineral hematite, and that was also verified by the infrared spectrometer. So this is what we saw from orbit that called us to this place, this mineral deposit occurring in these tiny little rocky grains. And they happen here on the Earth as well, these concretions. They form when water saturates a porous rock, and it's got cations in solution coming out of the rock, pulling iron and other cations out of that rocky deposit into a watery solution, and then you evaporate the water or have it slowly leave the system in a very slow and uniform way. And just like stalactites or stalagmites growing in a cave, minerals will precipitate out of that watery solution inside the rock, and they'll grow in these spherical grains. They call them Moki marbles here in the Southwest, if anybody's ever been to a rock shop, right? And here in the Southwest, they grow to be, ping pong ball sized. On Mars, on this place, they've only grown to be sort of ball bearing size. But it's evidence, and the rock itself is not a volcanic rock, it's a sedimentary rock that has water in its mineral structure. So there's evidence right where we landed that this watery past was going on there. We didn't know if that was a fluke place that we landed, so we drove to the next crater. This is about the size of the Rose Bowl football stadium. So it's a big, big hole in the ground with a big set of sand dunes inside of it, and very steep slopes, 60 to 90 degree slopes. But we could see these beautifully exposed layers on the inside of the walls of the crater, and so we had to get our rover driver friends, our licensed rover drivers at JPL, who are basically playing an interplanetary video game using yesterday's stereo models to simulate the terrain and drive a virtual reality version of the rover in yesterday's simulated stereo data, and then send those same commands to the real rover to get us around into these places. So we were able to do that very carefully over many, many days, because you can imagine you don't want to accidentally take a right instead of a left in this kind of a place. There's no way to rescue the vehicle. We're not in real-time joystick contact, right? You cannot joystick these things because we're 5 to 10 minutes away at the speed of light. So, but they did get us down into the crater. Here we are getting ready to go down there and waiting at the bottom, of course. So this is, it's hard to tell. It's like a 45-degree slope on plywood with ball bearings on it, right? And so kind of a difficult driving situation. And waiting for you if you slip and slide to the bottom is a rover death trap of sand dunes, which you can never get out of. So pretty exciting, but kind of slow motion exciting. They were able to do it and get us to avoid these sand dunes. This is exploiting the infrared capabilities of the camera. We can basically turn the long wavelength images into mineral diagnostic spectral parameters. So the deep red, the reddish reds here are oxidized iron, and the bluish colors here are less oxidized iron 2+. So we're making mineral maps out of those infrared bands. So it's absolutely beautiful, but very dangerous to the vehicle. So we can only approach them from a distance. But they did it, got us down on the inside of the wall of the crater. So we're on this inside this bowl, taking this panorama, looking around at this very steep angle, looking at these beautifully layered sedimentary deposits. These are the original, this is inside of an impact crater, so it's been fractured and broken up, and you're seeing a lot of the fractured debris. But then we're seeing below the fracture zone into the original subsurface, and these are lithified and compacted sand dunes that have been inundated with water and altered chemically multiple times. And it's loaded with those little blueberries, those concretions, and it's loaded with water-formed sulfur-bearing minerals. So again, that evidence of that watery past preserved there. So we drove to the next big crater, and this one's about the size of the ASU campus. So larger craters sampling deeper into the subsurface, going farther back in time. Drove up to the edge, looked for a good place to go in, stopping at each location, taking stereo images, building topo maps, trying to decide, can we get in, can we get in? Slopes are way too steep. Turned out the best place to get in was where we arrived. So we turned around, came back, just did a little toe dip into the crater, very steep slopes, difficult driving circumstances, again, with the remote control car 150 million miles away. Did a little way in and then departed and came back out. But went in far enough to make some pretty cool measurements, and I'll just show you some examples. This is just for scale. I put a CG version of the rover in here for scale, because there's nothing, you can't tell the scale in these pictures. Here's a rover for scale, here's a Buzz Aldrin for scale. You know, there's no trees, there's no houses, there's no tumbleweeds, no abandoned shopping carts, nothing. So it's really, really difficult to communicate the scale of some of these images to the public. That layered rock exposed in the walls of this crater, we're measuring its chemistry and mineralogy remotely and from fragments that are falling down and sitting at the wheels of the rover. Pretty spectacular terrain. Never imagined we'd be taking this kind of landscape photography with this vehicle. We went as far as we could go, and then we had to turn around and come out. And now we're getting to an even bigger crater. This one's called Endeavour. It took us about 3 years to make that drive from the last one I showed, which is called Victoria, to Endeavour. And you know, top speed of a Mars rover is about 4 centimeters per second. Look at it go. Woo. Very, very slow, and you can only drive for a couple of hours a day because of power. That's another limitation. But we got to the rim of this crater, and this crater is about the size of the city of Washington, D.C. So it's a bigger hole in the ground, sampling deeper into the subsurface. And we're seeing beautiful evidence of sulfates and clay minerals, water-formed minerals in this environment. So that's pretty exciting. And today we're exploring one part of the rim of that crater. We've just explored this valley. You see all the yellow lines we've driven around for the past year. Now we're going through that gap there, just gone through that gap into the next valley over where we see some different mineral deposits. Here's a picture that just came down last night. We're looking at drive direction mosaic and helping us decide, again, stereo imaging, slopes, and mix that in with the geology and the composition to decide where to go. So opportunity is still working great. and still finding evidence of that watery past. And then finally, Curiosity, right, in that hole in the ground with an enormous pile of sedimentary rocks. What is a pile of sediments doing there? How were they laid down? How much they tell us about ancient Mars? We landed on a fan of material coming out from the walls of the crater. Here's the landing site, also very flat, which was good. We could drive, use that mobility. The retro rockets scoured the ground, creating a big dust plume and getting the rover very dirty, but survived. Actually had one problem with one instrument because of the debris that was lifted up. And then we drove away. You can see the scour marks from orbit. So we have these orbiters that can monitor the rovers, and we use the orbiter data like a geologist would use air photos out in the field, same kind of thing. So we drove away. It was just actually kind of phenomenal how the vehicle was just set there by the sky crane maneuver by the engineers at JPL. I've driven across the plains here, heading towards the slopes, the lower slopes of that mountain called Mount Sharp, which is where we are right now. We've gone about 14 kilometers in the past 4 years. Here's a view. We made an instant discovery when we landed because those retro rockets blew all the dust away and exposed this coarse-grained subsurface. And this kind of looks like, when I broke up an old basketball court in my backyard, you get that conglomerate cement. You get chunks of rounded rock inside this matrix. Same thing going on here, except this is at the base of this fan of debris coming down the crater wall. And it tells us, and the rocks in this conglomerate are well-rounded, and it tells us that they were transported across a great distance. Too large to be transported by the wind, they were transported by water. So just from very quickly after landing, we realized, hey, you know what, there really was water in this crater. So these sediments are related to water deposition, and it was flowing at a pretty rapid rate to round these pebbles. And it was probably knee-deep or ankle-deep at one point in time, 3.5 billion years ago. So kind of exciting to make a very instant discovery. We've been seeing these finely layered sediments everywhere we go. So there was a rich watery past here. There was a lake here. Sediments were settling out of the lake gently onto the surface to create mud and mudstones and shales on the surface. Very, very fine-grained. It's a challenge actually for our cameras because the lamination size is comparable to the pixel scale. And so you start running into aliasing and other issues. We start running into problems with our compressor in the upper left there. If we send back the data even at JPEG 85, which is pretty high quality, but significantly less bits to have to send down, right? You can see hopefully some of the artifacts in there, color artifacts, stippling and zipper patterns and all the standard artifacts we're used to with JPEG. And so to do the proper scientific analysis on some of these places, we have to send the data back lossless. We just Huffman encode losslessly to send them back. And that's a significant hit in bits with that very narrow bandwidth pipe of a few hundred megabits a day coming back to the Earth. So it's always this constant challenge of figuring out how to manage our bit stream for that very small straw of bits that's coming back to the Earth. And sometimes we have to make these kinds of science trades. I can't analyze these layers the way I need to with all these JPEG artifacts. Have to send the full data down. And that means sacrificing something else going on that day. So Curiosity has been very successfully driving around, looking at these watery deposits, these mineral-filled veins, lots of evidence that there really was a lake in this environment. Curiosity can drill into the subsurface, not that deeply, like kind of pinky-sized drill, but the kind of cool thing is that once you get below the surface, red Mars becomes gray Mars. That oxidized outer layer, the rusty layer of Mars, really is skin deep, just skin deep in most places. As you go down, you reveal the less oxidized subsurface, and lots of these places full of clay minerals, which is very exciting because the clays have some of the water still in their mineral structure. So spending a lot of time with these imagers, characterizing the landscape, building these 3D models to help the rover drivers, and using the 3D data and high-resolution imaging data to help point the spectrometers, to help decide where to drill, get that sample into the organic chemistry lab and XRD inside the rover. So we've been following this path to the base of that mountain, and now we're at the base of the mountain, and we're crossing these big sand dunes that have been an obstacle to us, and we're starting to drive up. And so we're seeing these layers change as we go. And so now it's going to get very methodical. Let's measure these layers, chemistry, geology, mineralogy. Let's go to the next layer. Let's put the pages of the book together, going from oldest at the bottom to as high as we can go with this vehicle. Here's just a view from recent exploits. Again, sand dunes are bad. These vehicles don't have the capability to drive through sand like this, so we have to negotiate our way around them. We can dip our toes in and play with the sand a little bit because this is a very common material on Mars, so we want to characterize it. But notice how we've got, 4 or 5 wheels on the hard bedrock and just kind of dipping one in to very tenuously check it out. Here's just a recent mosaic. The landscape has been absolutely spectacular of late, very reminiscent of the desert Southwest out here with mesas and buttes and sand dunes and just some really spectacular terrain. Here's some very recent images from the last week or so with some buttes and mesas. Very fine layering again. Pages of a book, ancient lake bed deposits, lake floor deposits as we continue to drive up. So our goal is to drive up into that terrain, this terrain, as high as we can go. And you can see these layers. This is what we saw from orbit. This is what it looks like from the ground. This mountain is 4 kilometers high. And these layers go down to the millimeter level. So there's a lot of pages of this book to read. And it's just very exciting to be able to have a vehicle, a very capable vehicle with chemical and mineral and imaging capability on it to be able to make this study and test this hypothesis about the watery past. Just a few words here at the end about next steps, right? Some of you may remember the 1997 Mars Pathfinder rover was the first rover sent to Mars, and then Spirit and Opportunity landed in 2004, Curiosity in 2012. You can see which way the trend is going, right? What's next? That's pretty obvious. No. What's next is another rover called Mars 2020. And Mars 2020 will look a lot like Curiosity because it's built from something like 90% spare parts from Curiosity. Many of you know it's a difficult time for discretionary government spending right now. NASA's budget is very, very tight. And in order to get another mission in the queue, we had to go to NASA and say, look, it's going to cost much less than building a brand new rover because we have all these spare parts from Curiosity. So it will look on the outside very similar, but on the inside it's very different. It does not have that organic chemistry set or XRD. It has a sample caching system inside. So instead of drilling, we'll core, pull out a core, put it in a little tube inside the rover, and then take that tube and set it out onto the surface for a future mission to bring back to the Earth. So it's the first part of Mars sample return, robotic sample return, which most people think is an important step. Before we send people, let's get well-chosen samples of the place and figure out what that chemistry and hazards might be in that environment. We know there's peroxides there. We know there's extremely fine-grained particles, for example. So let's get a sample, and this rover is going to be the first step in that. So outwardly, it looks a lot like Curiosity, but inwardly and on the deck and other components have been replaced and upgraded. And we're very fortunate to be leading the effort on the new cameras here at ASU, the new color cameras, which are up on the mast there. We're going to do what we weren't able to do for Curiosity, and that is send some zoom cameras to Mars, so we won't have to deal with that one wide and one narrow focal length problems. We'll have 2 matched zoom cameras that will go from 34 to 100 millimeters. We'll do science with that imaging technology, fine scale textures, digital terrain models, multispectral red, green, blue imaging, the same kind of looking through the Bayer pattern now that we know how to do it well, and we can optimize that. And then we'll support operations, helping the rover drivers figure out where to go, where to put the instruments down, where to put the coring device to get those well-chosen samples. We want to pick 20, 30, or 40 of them, put them in these little tubes, and set those tubes maybe in one place or multiple places, kind of like the ultimate geocache, right? And then another mission in the 20s will go get them and bring them back to the Earth, or maybe 2 missions. That's TBD. We haven't figured that part out yet, but we want to do the first step. So here's just a quick advertisement for our cameras. We're calling them Mastcam Z because they're zoom cams. And here's a little animation. It is a difficult problem to build a zoom camera in a very small package Of course, companies do it all the time on the Earth, but they don't have to put those cameras on a violent rocket launch, and they don't have to land those cameras violently on another planet and operate those cameras over 120, 130, 140 degrees C temperature range in a very dusty and dirty environment. So all of those problems have to be solved, and we've got a very elegant solution. I can't show you a picture of the cameras yet because they are PowerPoint cameras. We have a critical design review coming up in about a month where we have to convince a group of about 50 extremely skeptical engineers from all around the country that we can build these things, that we've understood the problems that prevented us from building them before, and we're going to go forward with them. So maybe this time next year I'll have some actual pictures of hardware. But beautifully elegant design. We think it'll work very well, working with some wonderful engineers. We'll use the same Kodak detector. Remember, NASA's very conservative, incremental progress. The detector works fine on Mars, on Curiosity right now, does what we need, gives us the signal noise dynamic range that we need. So we'll proceed with that. Of course, this is part of a bigger picture. These rovers and orbiters and landers and the robotic work that we do is helping us understand this place. It's helping NASA get the information it needs to get people out there. And so what you saw in the Martian movie, I liked the movie because, there were some major science problems with it. We won't talk about those. But I liked it because from the technology perspective, it actually was a pretty accurate extrapolation of where we could be in the 2030s if we decide as a nation and with other nations to go that way. So the robotic probes are doing that for us, helping us get that information, the basic information about the Martian environment, about potential landing sites, about potential resources for people when we get there. And it's just wonderful to be part of a team here at ASU and around the country, around the world, that's using the robotics as the first step in that very exciting process. Thank you. Do we have time for some questions?
Maybe like
a couple of questions? Sure. I don't mind. Yeah.
I guess all the study says that there was a sign that there was water before Mars, but there is no water anymore.
Right. So,
How can you have life with no water?
so the question is, there was water on Mars, but there's no water anymore, so how can there be life? So a couple of things. There still is water on Mars. There's a lot of it as ice in the polar caps. There's a small bit as water vapor in the atmosphere. But where did all the water go that was filling these lakes, that may have been filling small seas? Some people even think oceans on Mars, although that's arguable. Where did it all go? We don't know. Missions are trying to figure that out, but it could be in the subsurface. There could be enormous aquifers or ice deposits in the subsurface. A key piece of information that's missing is what is the geothermal gradient? How hot does it get as you go down into the Mars surface? And there's a mission called InSight that will launch next year to try to figure that out, measure the heat flow, but we don't know the answer. But that exact question motivates us a lot because if there's no water, no liquid water there now, it's very hard to imagine there being any life on Mars. We know the Martian surface is devoid of life, and that's not surprising because of all the ultraviolet radiation coming from the sun. There's no ozone layer. But we don't know if you go down 100 meters, 10 meters, a kilometer, there could be a flourishing ecosystem down there. We just don't know.
So,
Yes.
More recently, there's been much more discussion about the Juno mission to Jupiter.
Yes.
Were you involved in that too? And how different is it because the environmental conditions are very different between those two places?
Juno is an entirely different mission to Jupiter. I'm not involved with it. But that mission is designed to measure the gravity field of Jupiter. In fact, there's a camera on that mission, but it's a very simple educational outreach kind of camera, not a scientific imager. I'm not a gravity science geophysicist, so I'm not involved with that mission. But that'll be very exciting to figure out, does Jupiter have a core, and what's it made of? It'll take another year or so for that mission to collect its data set. But I would be looking for, in a year, maybe 18 months, for some very exciting papers in Science and Nature all about that. Yeah.
Thank you very much.
Okay, thank you. Thank you all.
Dr. Wall.
Very nice to meet you.
And
Thank
we'd
you.
like
Thank
to-
you.
Very,
Oh,
very
thank you so much. This is lovely. Thank you.
to express our appreciation.
Maybe we can
Very
take
nice.
a
Oh,
picture.
yes. Let's slide that way a little bit.
Yeah, okay. Yeah, let's slide here.
There we go.
And maybe you're in the middle.
Okay. I'll try not to be so tall. Thank you. Thank you so much for the invitation. Appreciate it. Thank you. Thank you. So nice to meet you.